Today we were, I think, Pete, me, and 8 more people here. I see more people. 5 here, 10, and the 11th.
I think there's supposed to be 11. I think there's supposed to be 11.
We're supposed to be 11? 11 counting me or you?
11 of us, I think.
Okay. And I asked you the other day what was your background, and I heard that pretty much half of you are mechanical engineers, and half of you are astronomers, astrophysicists. So we're going to work with light and instrumentation. So I guess both sides will be interested, and I'll try to make it accessible for everybody. If you have any question, don't hesitate to ask. I'm going to open the presentation so I can see it myself. Could you guys access?
Where's the presentation on Altima?
Resources.
So membership, this class, resources, week 3.
Okay, I found it.
Yeah.
It's not open. Okay.
Now we are 11.
Okay.
Can everybody see it? More or less? Okay. Like I said, we got introduced the other day. I'm Tyro. I work here at HIGP. I graduated here in the University of Hawaii with my PhD on the former geology and geophysics. Prior to that, I studied physics. I was always interested in geology, physics, astronomy as well, and in planetary exploration. And I do have the privilege now of working for the Perseverance rover with the SuperCam instrument, which is a remote sensing instrument that uses Raman spectroscopy, mainly Leaves spectroscopy, where most of the data is coming from. And it performs also fluorescence measurements that we will see in the class, and it does also visible and near infrared reflectance that I think you're going to study with Rob Wright. And has a camera to take pictures and a microphone. So we are doing great science there. We get a lot of data every week from Mars. And in this first slide, there's a picture of the mast unit of the SuperCam instrument that has a telescope where the camera and all the spectrometers are connected. So that's where the light from the measurements is gathered, and all of it is integrated into the rover that has different units of payload hooked into a main computer powered by a small nuclear reactor, and is investigating now the Zero crater in Mars. For this class, we are going to study vibrational spectroscopy, which includes Raman and infrared spectroscopy. Infrared spectrometers are big and bulky. It's very useful, but not very useful for in situ planetary exploration, not usable yet. So we'll study Raman spectroscopy. From those, the vibrational spectroscopy, and then we'll see atomic spectroscopy for LIBS, which is laser-induced breakdown spectroscopy, and then we'll see a little bit of fluorescence spectroscopy. We'll study a little bit of theory and a little bit of instrumentation, and then, like I said the other day, we'll go to the lab to take some measurement and see the actual instruments. And also, like I said, I hope everything makes sense at the end of the class. So for the first class, we're going to focus on vibrational spectroscopy. And for all these spectroscopies, both vibrational, atomic, and fluorescence, we're going to be dealing with light. And I would like you to have some basic knowledge of what is light. And I'm sure the astronomers know. Is that correct?
Electromagnetics.
Wavelengths?
Yeah.
Electromagnetic radiation, right? It's a form of energy where electromagnetic energy is propagated through space, yeah? And do you see light? Obviously we see light. We see all the light? No, we don't. We see visible light, which we all know is all contained within violet and red, right? Which correspond to, I don't know which frequency of light, but between 400 and 700 nanometers. The frequency numbers are very big. There's light on both sides of what we see. If you think of a laser pointer, I'm sure you've seen red ones, which are usually 632 nanometers. That's what we see as red. I'm sure you've seen green, maybe. Those are usually 532 nanometers, very similar to the lasers we use. There are some blue ones, and lasers are fairly monochromatic, meaning they have one distinct color. However, the light that we see is usually white, or we make it look white, which is what our brain interprets from the signal from our eyes as a mixture of all colors. So we'll try to see what all that is, and what produces light. So that will be energetic processes which involve charges accelerating and decelerating and moving and vibrating in general. Those can be molecules or electrons, particles, right? Protons. And when they move, accelerate, decelerate, they will radiate energy as electromagnetic waves. In the case of the lamps here, that's fluorescence, electrons jumping from orbitals in the atoms. On an incandescent lamp, that will be molecules vibrating, thermally vibrating, because of the current that will run through them. It will energize and accelerate. And those waves, the light propagates through space. Yeah. The light through experiments we learned mainly in the last 120 years that is both a particle that we usually call photon and a wave that propagates through space and follows most of the rules that applies to waves, such as sound or ocean waves, but also rules that apply to particles in terms of scattering. When things hit each other, they behave like particles, or when transmit energy to extract electrons from a surface, something like that, the light becomes behaves like a particle that we call photon. So the photons have an energy that translates into a wavelength, a frequency, and those are characteristic to the photons. We'll see all this again, so I hope that becomes very clear. And the complete spectrum of light, so we have visible light, which is what we see, and the complete spectrum is the electromagnetic spectrum. Are you guys on the whatever slide it is, which is the third? Fourth. Where we have a nice picture of what the electromagnetic spectrum is. So in the center, represented as a rainbow, we have the visible spectrum, contained between 400 and 700 nanometers. And then on both sides of the visible spectrum, we have very familiar, I guess, I hope, names, which are the infrared and the ultraviolet. The infrared is below the red, and the ultraviolet is above the violet. You can think about it as energy. So above the violet, we have more energetic electromagnetic rays, waves, that are known to burn our skin, that cause damage. They have more energy than visible light. And conversely, in the infrared, the photons will be less energetic. And there are even more energetic and less energetic phenomena that produce electromagnetic waves on both sides of the spectrum. We are familiar with microwaves and radio waves, and also X-rays. Maybe not so much with gamma rays. We don't use gamma rays in daily life, I guess. But they do arrive on the Earth, and they produce what they are called cosmic rays. They produce radioactivity, like cascading particles in the atmosphere. They produce on very energetic stellar processes, right? Astronomers there. Not so much on the Earth, except on radioactive decay, which is dangerous, like you know, so it emits either beta particles, which are electrons, or alpha particles, which are helium nuclei, or gamma rays, very energetic rays. X-rays are very energetic. Those are all very familiar with. They go through our flesh with no problem. Not so good to our bones, so we can see inside, taking pictures to contrast, and that's how we see our bones. They are obviously dangerous too. Ultraviolet, they all have big ranges, yeah? They're most energetic, less energetic X-ray, more energetic, less energetic ultraviolet. The ultraviolet rays that goes through the atmosphere are what they call the UVE, A, B, and C. Each of them being more energetic. Most of the rays we get are UVE, a little bit of B and C. Hence they sell this broad spectrum sunscreen that's supposed to block all of that and either absorb it or reflect it, so it doesn't have the chance of burning our cells and mainly our DNA and possibly produce cancer. Infrared, microwave, and radio waves are less energetic. We also use them in daily life. in daily life. Infrared, we do feel it mostly when something is hot. You feel, if you touch it, you'll get burned by thermal conduction. But you also feel the infrared waves hitting your hand. If you approach your hand to the electric stovetop, you'll feel it heating up. When it heats up, it will produce more and more infrared, and when it heats up more, it will produce that red-orange glow that we see, which is the spectrum emitted from the stovetop peeking into the visible. We start seeing it in the red. The rest is infrared. Pretty much everything emits infrared. This is DAB thermal radiation, I guess, because we can see difference in temperature if we can take a picture with infrared light. In this room, for example, we will look bright in infrared light, and the furniture, the walls will look darker in infrared light, because we are basically hotter. Then microwaves is a big range of less energetic waves that we all know from the ovens, in which a particular microwave energy wavelength matches some resonance vibration from the molecules of water. When you put your food in there, provided it has water, you bombard it with that particular microwave, and that will move, and moving will heat up, transfer its energy as thermal energy, and heat up surrounding proteins and sugars and whatever is in the food. Will heat up the food, provided it has water. And then microwave and radio waves are also widely used because they go through us, they go through walls, they go through the atmosphere to higher or lesser degree. They are very useful to transfer information. So radio, old-style television will travel through radio waves. The telephone signal will travel through radio waves. And I hope you're all familiar with it. Yeah? So in terms of frequency, we have very big numbers, which I don't know by heart. In wavelength, we have more attainable numbers that can range from meters, big waves, infrared, not infrared, but radio waves, into very short atom nuclei size waves from X-ray and gamma rays. And then on the Earth, we see visible light. Fortunately, our eyes adapted to it through evolution. We see very well the light that is most readily transmitted through the atmosphere. The sun is glowing in kind of in ultraviolet light, with a lot of visible light, some infrared, and not so much of the more energetic radiation. And then our atmosphere is transmitting mostly the visible and radio waves, and is blocking most of the ultraviolet and all the other things, and a big chunk of the microwave and infrared. Astronomers will know that to see those wavelengths, we'll have to send telescopes up to space. And we'll see a little bit of, the stovetop heating up and turning red, which is called black-body radiation. And all these wavelengths, the electromagnetic spectrum, can be associated to thermal energy as well, and there is a correlation between the light they emit and those bodies that have different temperatures. So it follows that hotter bodies will emit more energetic radiation, and cooler bodies will emit less energetic radiation. And that will be the black body radiation. If you take the sun, for example, which surface is at 6,000 Kelvin, give or take 6,000 Celsius, it'll glow mostly green and yellow with good amount of ultraviolet, and then a big tail into, we have in the x-axis, we have 0, 500, 1,000, 1,500, and 2,000. That's the wavelength in nanometers in this plot. The visible range is between 500 and 700. To the right of it, we have the infrared. To the left of it, we have the ultraviolet. So the sun, which is at 6,000 Kelvin, we have a curve here for 5,500 Kelvin. It emits mostly green and yellow with some ultraviolet and a lot of infrared. That goes through the atmosphere. Most of the ultraviolet gets blocked. So we see that white, yellowish sunlight, which is what our eyes interpret as that light curve getting into our retina. Colder bodies will have a spectrum that shifts to their right and becomes less intense, but it does shift to the right. So colder bodies, they still emit most of their radiation into the infrared. Can get as cold as the universe, which emits radiation at 3 Kelvin, right? Is that correct? Do you guys know?
Say that again.
The universe is at 3.5 Kelvin or something like that, and it emits how is it called? The microwave background. That's the black radiation of the universe. Very cold. We see the stovetop, yeah, with certain temperature, and then we have hotter things, yeah, stars or filaments that we use to produce X-rays, things like that will emit higher wavelengths. And all that is emitted as a continuum spectrum that really turns out not to be continuum. We'll see that it looks continuum, but then when physicists try to run experiment and test the assumptions that it's a continuum spectrum, things didn't add up, and that gave rise to all the quantum theory, in which all the energy there is distributed in small packets of quantified energies, and that applies to everything. On bigger things like us, we don't see it, but when we deal with molecules and electrons and smaller things with less mass, then it becomes very apparent that there are energy gaps. We'll see that on fluorescence, Raman spectroscopy, and atomic spectroscopy, where we'll see that the emitted or exchange energies are quantified. That's how we can tell which atoms or which molecules we might be looking at. And I guess it's pretty obvious now how come I don't see the room glowing. it is.
Our eyes are only sensitive to visible light.
Correct, and the room is emitting mostly infrared, yeah. The room is at 300 Kelvin or so, so the curve will be very flat there. Will be emitting infrared and not so much energy. And we won't see it until it heats enough to produce visible light. So we will not see anything with longer or shorter wavelengths than light. On the next slide, we have a similar graph to the blackbody radiation, but for much higher energies. Molybdenum is a metallic element, that's a heavy element that we use to produce X-rays. And we pretty much heat it up, provide energy to it by running current through it with very high energy of kilovolts. We have on those curves, we have different kilovolts. On the x-axis, we have again wavelength, but now instead of nanometers, we have angstroms, which are 1/10 of a nanometer. A meter is a meter, a nanometer is 10 to the minus 9, so 0.8 zeros and then a 1. Meter, an angstrom is 10 to the minus 10. So when the molybdenum gets heated up by the current, it will emit something like a blackbody, but a very much higher energies into the X-ray range. The higher the current, you'll get more temperature, and you'll get a curve that is also broad, and that is shifts towards shorter wavelengths, more energetic electromagnetic radiation with the higher temperature. In the case of molybdenum, you'll get also this characteristic radiation, which are basically atomic emission lines from electrons that get kicked out from inner layer orbitals of the molybdenum atoms, get energized out, and then when they come back, they emit the difference between whatever level or outside level in the atoms they are coming back and those more energetic inner orbitals, and emit characteristic wavelengths, energy values for those difference. That will happen to every element. We already talked about the next slide. Yeah, very simple with a rainbow put in there. You are all familiar with the rainbow. The rainbow, we see many of them in Hawaii. The rainbow is an electromagnetic spectrum of visible light. The visible light, the light basically that we can see that goes through the atmosphere, it gets refracted twice and reflected once in the droplets of water. When it refracts, it undergoes dispersion, which we'll see a little bit of, in which different wavelengths will bend more or less depending on their wavelength. So the colors, the different wavelengths, will separate, and when it comes out of the droplet in our direction, we'll see a rainbow, which is a visible spectrum of the light. We see that is a continuous spectrum, we actually can do spectroscopy with our eyes. We'll see that. We do have 3 different filters in our eyes that our brain is taking information from and processing each color from whatever we are getting from those filters. We'll see that in the laboratory we will use a prism or to induce refraction, or more commonly a diffraction grating to bend the light and separate the waves to see the spectrum. The rainbow is of course nice. You need a proper alignment between the droplets of water and yourself. And the center of the rainbow, if you look closely, will always be on the line that the sun forms with your head. So when it's morning time or sunset, you might see the big rainbow on the other side. When it's midday, we probably won't see many, because especially in Hawaii, we have the sun very high up. The rainbow will be in the floor, and we won't see it there. If you were on a plane and the sun was behind you, you could see. Actually, can be seen a rainbow that is round. The sun is standing behind you and it's raining. You'll see that. We see in the slide, we see the same thing with a visible spectrum overlaid on it. And we also discuss how at room temperature, mostly the maximum emission is in the infrared, and that will be the principle that night vision cameras and thermal vision cameras use, in which we will, like in that picture, we will show up bright with respect to the background. We will show up bright on this kind of images. We see 2 kinds. One that is kind of like green, the green image that might have brighter objects, which are the harder objects. Yeah? Those are usually night vision cameras. And then these blue, red, and white kind of plots, in which typically more intense is represented as red, and less intense is represented as blue. Some other animals, they'll see different ranges. Night vision cameras, thermal imaging, and then the next slide has our eyes. I did mention that we have 3 filters. Not really filters. What we have filters are the actual instruments. They do have filters. They can do spectroscopy with filters. We can do spectroscopy with our eyes. We do have 4 kinds of cells in our retinas that allow us to see. Some of them are called cones, and some of them are called rods. The rods are very sensible to light, but they have no filter. So basically we see all in the same color with the cones. They are very sensible to light, so those are the only ones we can use when it's very dark. And we just see bright or less bright objects. We cannot see colors when there is not enough light, but when there is enough light, then the cones start sending signal to the brain. And each of the 3 different kind of cones has a different wavelength sensitivity range. That's what I call filters. There are no filters, it's just a sensitivity range from our cells. And there's a plot on the bottom left that has the curve of the ranges that we have in our cells. And as you can see, they are pretty broad and overlapping. So we have a kind of like blue-violet kind of cone, a red kind of cone, and a kind of middle of the range that's called green there. Kind of rod. You can do spectroscopy. Actually, one of the payload of the Perseverance rover, which is the camera, can take pictures with different filters. So because intensities are different wavelength ranges, so it can extract some chemical composition from there. Yes.
Oh, I was thinking the cones are really like filters that we use to when we look through a telescope to extract a certain light.
Yes.
Is that correct?
I think so. Yeah. In astronomy, you also take a spectra. Yeah.
Yeah. So
With
we
a spectrometer, but
use filters.
you will use filters. Yeah. Yes. So we have those three cells that are picking up different intensities on those different cells, and all that is sent to the brain, and then the brain does all kind of things to make us see what we see. Probably we all see different things based on our cultural background, but there are some biological constraints that make us all see about the same. When all the filters get excited more or less in the same amount, we see white. Yeah. We see white, whether it's the sun or incandescent lamp, which we saw as a mixture of colors, yeah, the rainbow put together, yeah. Whether it's that or these lights here, which are white too, but they are not continuous like those plots we've seen earlier. These lights here are called fluorescent lights, and they have a tube that has two electrodes on both ends, and we're connecting the electrical cables there on the ends. So there's a current, like AC voltage applied to it, a current going through a mercury atmosphere, very low pressure mercury atmosphere, in which the electrons within the mercury will get excited and preferably produce the recombination emission at 253 nanometers, which is ultraviolet. We will not see, but that will glow inside the tube and hit the coating that it has, which is a fluorescent coating, in which the electrons within the molecules will excite and relax and emit some energy on the wavelengths that we can see. And if you can see spectrum of that, you'll see that it has a line at 546 nanometers, which is green, and then a little bit more, which is the green, 140. This is going to be green, yeah? And then a little bit more oranges at a little longer wavelength, and then some bumps from the fluorescence in the blue, a little bit in the red, those lines all mixed together. We see white, and we all know that the white we see here is not the same as the white we see outside or with different bulbs. That all comes from our cells in different ranges. We'll see in, if I forget to show you, you remind me. We'll see in the lab that although we are supposedly only being able to see down to 700, we can actually see a 785 nanometer laser beam, and it looks just as red as the 633 because it's citing the same filter. And then, like I said at the beginning, the eye color sensitivity, there's another plot there that indicates that our eyes are very sensible to the green and yellow parts of the spectrum. And I did say that that's probably because of evolution. We evolved to see better in the light we have, which is the sunlight. So we see a little bit of violet and blue, a little bit of red, and a lot of green. Yeah, so when we see at night and we can barely see, whatever is green, we'll see it better than violet things at night or red things at night. And then on the next slide, we have a little bit of how those filters might work, whether them working by reflecting or absorbing light. When light gets to matter, it interacts with it in different ways. We'll see that. And one of them is absorption and reflection. So for example, when we see something white, provided that we have a white illuminating source, we can see that the surface is reflecting more or less uniformly across the visible spectrum. If something looks red, we know that it's absorbing things that are not red, things that are blue. As long as something is absorbing blue, our eye will see it as reddish. If it's absorbing more blue, more green and yellow, it will look more reddish. Conversely, if something absorbs red, it will look bluish to us. And if we have addition of wavelength ranges, such as in the left plot, we'll have those filters in there that are commonly used because they mimic our sensitivity in the eye, so we can make screens and make things that we can see that they look to us like real things. That's why we use that green, red, and blue. They are designed to mimic our eye. On the computer screen, the little emitting screen pixels have those filters. When they all light up, the screen looks white. When it wants to make the image look red, the red pixels are brighter, the other ones are darker, and conversely it makes the other colors and the mixture all of them. Yeah. If we mix the same intensity of green, red, and blue light, we'll get yellow for green and red. Whatever our eye will see as yellow, we'll get that cyan color between green and blue, and we'll get magenta, some violet hue between red and absorption filters, such as in reflecting things. We'll see that if we absorb a combination of wavelengths, we can get different colors, yeah, such as red, green, and blue, stemming from the other ones in the other plot, which are yellow, magenta, and cyan. And of course, when something absorbs across the range, such as these chair backs or your t-shirts, YouTube t-shirts and tank tops, it's absorbing across the range, so it looks black to us. The paper or your shirt will reflect. Variably, your red sticker will absorb the blue. Actually, will absorb the yellow and the violet. I wrote here, yeah, I did talk about screens. Yeah, screens, the cameras that we use, the sensors that they have frame filters, so they can record in the data as numbers, whatever the screen has to later make it, right? So we can see whatever picture we want to see or the spectrum we want to see. And then we have subtractive, which are the dyes and colors and I don't know, the colors that are there. Yeah, water looks blue to us because of absorption. The plants look green to us because of the same reason. And for all nature things, I guess the source of light is the sun. Everything you can see out there, there's absorption. We did see the black body radiation. So we said, I said we can make some spectroscopy with filters. Yeah, crude, but can be done. You can do some spectroscopy with just the black body radiation. That's why we know how hot stars are. Yeah. Some stars look red. Some stars look like our sun. And some stars look fiercely white. Yeah. And even bluish. When they are bluish, I guess, correct me if I'm wrong, they are very hot. The peak is probably on the ultraviolet or somewhere there. And in the visible spectrum, most of it is in the blue, not so much in the red. So it looks to us blue. I put some numbers here, mostly regarding the sun and your stop, in which at 400 Celsius we'll start seeing that red, orange, and it will not start becoming more yellowish until we start getting some more light into the other cells, the ones that see the green, which will happen at 600, 700, 900, and then as this gets hotter, it'll become white, yeah, when the curve goes all over our range. Let me think out loud here. We start at 10:30. We have from 10:30 to 1, which is 10:30, 11:30, 12:30. We have 2 hours and a half. So we'll make a little break about 20 minutes from now. if that's okay. If you have any question, of course. Might be a lot for some people, maybe not a lot for other people. So now that we know a little bit of what might be. We talked about energies that are related to colors and wavelengths and frequencies. Those are all related to each other. And it can be used to perform spectroscopy, which is what is going to matter to us for planetary exploration. And there are different kinds, right? Gamma ray spectroscopy you'll study with Peter. Yeah, more energetic processes. On planetary surfaces, right? X-ray as well. The gamma rays, I said, they are produced by very energetic processes, such as, I don't know what happens in stars, I guess explosions, supernovas, and things like that. And on radioactive decay, you know, when nuclear strong force gets exchanged between molecules, very high energies might get released, including gamma rays. X-rays are less energetic, still very energetic. They arise mostly from emissions from inner electrons in atoms. In atoms, inner electrons are more strongly attached to the nucleus, so it takes more energy to take them out. When electrons come back, they release more energy. When they jump down to those, they release more energy than they will do from outer layers, less attached. And there's a bonding energy between electrons, and we'll see later there's a bonding energy between atoms as well when we study molecules. So X-ray will arise from more energetic atomic electronic transitions. The ultraviolet and visible range will arise from valence, so outer electrons in atoms and molecules, and also tightly bound. And then infrared light, which will fall in the range of Raman and infrared spectroscopy, will arise from less energetic processes, which are vibrational energies. We'll see that. I'll repeat. When things are hot, and everything is hot, because nothing can be at 0 Kelvin, everything has to have the temperature. They will have some vibrational energy, in which atoms and molecules are thermically vibrating. That will make it hot. And those transitions, those energies, like I said earlier, they're going to be quantified too. So the transitions between those vibrational energies, when they are going to fall in the infrared, there are less energetic processes that can be used to obtain information, such as microwave, that will arise from rotational energies. Rotational energies are basically molecules spinning. That has less energy than electrons jumping on and off, or molecules vibrating. And then there are some other spectroscopies related to atomic nucleus, that can be made vibrate with different energies and see their response. Those are the electronic spin transitions and the nuclear magnetic resonance. nuclear magnetic resonance has been used for planetary exploration as well. In the first missions, the Spirit and Spirit and Opportunity, Mars exploration rovers. And the first one, the Sojourner, I think had some very crude one. And to close off, not close off yet, but familiarize ourselves with light. I put a lot of things here to have a kind of informal discussion about all the things that can happen to light when it interacts with matter. There are many things. One of them everybody's probably familiar with is reflection. Very obvious in a mirror. Light will get specularly. Speculum is the same as mirror, Latin I guess. Will get reflect as straight rays, and we'll see our image in there. From a metallic surface, we'll get that kind of reflection. We do get reflections from, non-polished surface, which will diffuse in the sense that one ray will get there and it won't get symmetrically reflected with respect to an angle. It will go in all directions. Depending on the surface, it will disperse more or diffuse, not disperse, diffuse more or diffuse less. There is refraction that probably everybody is familiar with. We talked about the refraction in the droplets of water that forms the rainbow. We can see refraction on a surface of water too, when we have an interface between two media with different refraction index, two media in which the light travels at different speed. In surface of water, one media will be the air, another medium will be the water itself. And when we see through water, we see the light coming from whatever is under the water, the fish or whatever toy we drop there, and where we see the object, where will not be where it actually is, because the rays that are coming from that object towards us, they actually bend at the surface. So when light goes from one medium to another medium with different refraction index, with different speed, the light will bend unless it goes straight in. If it goes straight in within the media, it will go straight. But if it comes at an angle, it will bend. It will bend more or less, depending on wavelengths. That will give rise to spectral dispersion, which is what makes the rainbow, and how our spectrometers will work if we were to use PRISM. Whoever studying physics, astronomy, might have seen some physics with PRISM. Maybe engineers not so much. I really wonder. You can see it on the Pink Floyd cover. I've seen that in t-shirts. Very famous image in which you'll get a white beam going through a piece of glass. Yeah, that is angled in the proper way, so when it comes out, it comes in the angle where you want. If you have a surface like this, it kind of wouldn't work, because you'll get the white beam going through, so it will look white, yeah. But if you angle it, you'll get the dispersion in the first phase, where light will go in and bend. If it's blue, it will bend more. If it's red, it will bend less. Go through another interface on the exit and disperse again there. And at the end, you will end up with the red in one side, the blue on the other side, and get a spectrum like that. That was used to make spectrometers in the past. It's used in, I guess, schools to demonstrate. But for instrument stations, we'll use diffraction gratings to produce dispersion. Absorption is basically what it says, absorption of light. The materials will absorb different light depending on what they are, their chemical make, their chemical properties, and that can tell us a good deal of what the materials are made of. That's going to be the reflectance and infrared reflectance, visible infrared reflectance spectroscopy that can be used from satellites to study large surfaces of planets and monitor the Earth as well. Some things absorb more. Bleach paper reflects a lot. Yeah? Mirrors reflect a lot. Black things absorb more. Yeah? They will get hotter when irradiated with infrared light, yeah, regular light. And yeah, so different geologic materials will have different absorptions. And then we have diffraction, which is what the light does when it goes through an opening. When the opening is big, like a door, we will not really see it. But when it's very small, matching the wavelengths of the lights that we are looking at, it will actually bend, and we can see that bend. So I guess some radio waves will actually bend through the door. But to see visible light bending, we need kind of like 1,000, 1 micrometer openings, and the diffraction gratings that we use for our instruments, they'll have edge, either reflecting lines or transmitting lines that are very closely spaced, so they can effectively diffract the wavelength range of interest. You can actually see that for visible light on compact discs and DVDs. In compact discs and DVDs, the data is written in spirals that are very close, packed together, about 1 micron width or even less, which kind of matches the range of wavelength of visible light. So you guys can, if you're curious, you can make a spectrometer with a compact disc or a DVD. If you look, I'm sure you've seen it, if you look at compact disc DVDs, you see rainbows of them. Usually you'll have light coming from all angles, so it will look like a mess. You see some reflection of the first order, in the first diffraction order, you'll get a reflection from the surface, but you'll also get diffraction from different orders. You see different wavelength ranges. If we do it here, we'll have all these sources. We'll have light dispersion everywhere. But if you were to get far from a source, doesn't have to be too far. It can be that light there if you have the compact disc here, meaning the size of the object is kind of small given the distance. If you look at it at the proper angle of the compact disc, and you have a light, you can see the spectrum of the light through diffraction there. If it's don't do it with the sun though. If it's don't do it with the sun because you'll get the reflection of the sun into your eyes, which is no good, or the first order diffraction of the sun, which is going to be very intense. It's going to be very intense. It's going to have a lot of yellow, a lot of lot of green. It's going to go straight into your eye. But if you do it with a old bulb, you can see that black body radiation for the bulb. You can see a rainbow. If you do it with these lights, you'll see those little patchy red and bluish things. Many of the things are LEDs nowadays, which will have some other colors that are made with PN, like transistor junctions, where there is an energy gap between the electrodes, that in those LEDs have the potential of emitting light corresponding to those energy gaps. That's how LEDs are made. But if it's an old gas emitting lamp, one of those that is orange, you can see that it's actually orange, and you can see that instead of a rainbow, you just have two close lines in the compact disc. Of course, the compact disc is not a diffraction grating. In our instruments, we have straight diffraction gratings. On the compact disc, the data is written in circles, so you'll see all that in circles. That is diffraction. Like I said, it happens when a wave goes through an opening. You can see that on ocean waves as well. It comes from the wave nature of light. You can see that on ocean waves or on sound waves when they go, ocean waves when they go through a corner of a pier, the wave plane will hit there, get reflected on the pier. You see waves reflecting, and you'll see waves going straight and also bending a little bit at the edge, because they are going through an edge, through an opening, and there are 10 meters, 20 meter waves. The same happens to light, and interference is closely related to that. It comes also from the wave nature of light, and it will arise from electromagnetic waves adding and cancelling each other. We'll hear interference on the radio when things mix together, when the signal is low. We'll see interference when there is some oil floating on water. We'll make very thin layer, and the light will reflect off the first phase and the second phase, and come to you as reflected from different distances. So when that happens, the light that's coming to your eye will be interfering with each other. So you'll see rainbows there too, from the white light spectrum, like cancelling and summing each other. You can see that on Diamond Head. If you look at the lookout, you see waves reflecting from one side, the other side, mixing, and you see places where the plane waves out of the ocean come flat, and then they hit the shore, they reflect and disperse, or they hit a rock, and then they reflect like this, and that hits the incoming waves so close to the shore. We see choppy water, which is the waves adding adding and subtracting each other, and also reflecting of the water. We can see that. Scattering is what we see for Raman spectroscopy, which are basically when light behaves as a particle and photons hit things, might kick them out, accelerate them, bend on them, change direction when it hits something. So scattering will be the change of direction when it hits something out, namely an electron. That will be the photoelectric effect, where light with enough energy can potentially extract electrons from materials. And if it doesn't have enough energy, it's red or lower radio waves, you won't get that. We'll see fluorescence as well. That we said it comes from the interaction of molecules, the electrons in the molecules with the incoming light. And what will happen will depend on the nature of the material, the nature of the photon, of course, the smoothness of the surface. It will reflect specularly or diffuse, depending on how it is. And then some random things I put here. You see an antenna there that's made of wires. That wouldn't work for visible light, because the visible light will go through it. But it does work for radar that has longer wavelengths. So the longer wavelength won't see those openings there as anything inside, so it will actually reflect. When you have normal rays, it's easy to transmit light. When things come at an angle, they are more likely to get reflected. And then some weird things that we don't are familiar with, I think. But if you got light, for example, coming from water to air, so from a higher refraction index to a lower refraction index, you can see the light, if you shine it, will go through, but if you put it at an angle, you might actually find an angle at which no light goes through the other surface. That's total internal reflection. And for any light, you can find an angle in which some polarization of the light will actually get transmitted and the other one reflected. This polarization is, we're not going to touch too much on that, but the electromagnetic radiation of the light has a magnetic field that oscillates on one plane, and electric fields that oscillates in another plane in regular normal light. I guess all those planes are in all kind of directions for all the waves, but in polarized light you have the waves perfectly aligned in one direction. Then I have here the Pink Floyd picture, so you can see the dispersion on a prism. That's again what happened in the water for the rainbow, and that's how we get the spectra that we work with. The index of refraction will be the ratio between the speed of light and the speed of light in whatever medium. The speed of light in a vacuum or in the air is about 300,000 kilometers per second, something like that. It travels slower in other materials, in other transparent or translucid materials, such as glass or other minerals. The refraction index is the ratio between those two, and that can be expressed there as a function of frequency of the light and wavelength. So the energy of a speed of a photon in a vacuum will be it's the the frequency and the wavelength will be its speed in a vacuum and in different media as well. And the index of refraction will be inversely proportional to the wavelength, which will mean that the blue in the visible shorter wavelengths will have a higher refraction index for a given media and will actually bend more at the interface. And then we'll move into vibrational spectroscopy. It looks like I'm doing great with the time. I said 20 minutes, I think it's been 25. We got to the second part, so I'm going to stop 5 minutes. You guys need? I need. I'm talking. It's a little tight. I'll be right back.
I just I know, but I don't know how to write on purpose like that. I mean, you can do it.
Oh, I'm so
You
used
know,
to
you
it
know,
now.
Leah.
I know Leah.
Like you can write notes. I just kind of
Uh-huh.
like it's writing. I can't write that on paper like this. So.
I write faster off.
Yeah, you're crazy. I mean, really? Is that just looks like prints?
It's faster to write on the iPad. It's smoother.
Sleep. I drifted in and out.
I was young.
So we're meeting over Zoom today at 4.
I think we're all, coming in here.
We're coming in.
Zooming
Okay.
to Professor.
Okay.
Yeah.
I can't come in, but I might have to leave pretty quick because I gotta take my girlfriend somewhere. It's not gonna be like this every week. This week. But I might be able to come back if we end up like doing stuff.
I think we're more so probably talking about timeline.
Yeah.
Is my best guess.
Yeah, I want to try and. Sorry, I'm like super nasally right now. I have shit on my nose. I want to try and finish off the design a little more of what I'm doing, but and then once I have that, I want to figure out a way to print it,
Yeah.
and then think about with what's her name, the other girl, Savannah. How to incorporate the gamma ray.
So are we incorporating the gamma ray
Yeah.
into our project?
It has to be both, is what he was kind of saying. If we ever want to like have lunch, I
Oh,
think,
How does that work with the internship?
you mean with like it being
Like with the funding?
that's,
it's confusing.
Yeah.
So is it like double funding for this one project? Because she has funding for that.
I know
And we
that's
have
weird.
funding for this.
That's true. That is weird. But he was saying that he wants us to work together to like design the actual like satellite interface because obviously each part is gonna have their own like necessities, and I can almost guarantee there's gonna be some parts of the neutron, some parts of the gamma ray that are not gonna want to work
They're not,
together.
yeah, exactly.
So- And in a 1D, which is 10 centimeters by 10 centimeters, putting all those electronics for both of those two, because you'll need 3 photodiodes, because you need 2, I think, for the gamma ray, and then 1 for the neutron,
Yeah.
because the gamma ray is 2 scintillators, because it has it does the one where it's like minusing.
Oh, okay.
The neutrons you don't have to do that with though, but I'm pretty sure that's what she was planning for the gamma rays.
So how about
So you would need at least 3 photodiodes, which means that the PCB that it would be put on, I don't know if it could, like I'm kind of concerned about power too, because running all of that,
I didn't know I thought we were just like working together
Yeah.
for 2 separate projects.
Not
For,
aware.
I didn't know we were merging.
Well, I don't think we're merging yet.
Okay.
I think kind of for the funding we have to like do the neutron ourselves for
Okay.
now. But I think in the future,
And-
probably next semester, he wants us to be.
Merge it.
Yeah.
Like one big type of
So how do
detector. One big payload. Is that what we're thinking?
So what is that, the event that day, night, Friday night, what was that? Something like that.
Oh, it was just our orientation.
Oh, yeah, but what does the internship offer?
Money to fund it,
Oh,
to pay for it.
but not for the individual, for the project.
No, both.
Oh, okay.
It's a
alright.
paid internship, yeah.
So I don't
Although the funding for the project's not that.
yeah, I don't need
Yeah.
funding for me, but
No,
the funding for the project.
We have it already,
Yeah.
yeah.
Yeah, I like this.
What?
No, I like this.
Oh, yeah.
Oh. Yeah, I mean, how can you do it? She just drew this on the fly.
Oh
I
my
mean, like taking notes. Just,
Oh, wow.
You can just print it
We
and
have like a
publish.
5-minute. I had time.
I can't do it in an hour.
That's really nice. Maybe
Yeah,
I can borrow it from my
Yeah,
presentation. also.
Yeah, can I have your notes? And it's just like printed, isn't it?
Yeah.
I know people like that. That's
Wow.
what colleague get. You know, when I was at the IFA,
Mhm.
she writes like, she sent you a card. You didn't remember that she wrote it. I said, where did
It
you
looks
buy
printed.
Where do you buy a card like that? So I wrote it.
I should have gone into the art department. Should have majored in
But-
art.
Well, you can still do that
Yeah.
as a hobby. It's better because art you don't have any guarantee that you'll be successful. But this you can be successful. Yes, we do it.
Maybe, right?
Huh?
Maybe.
Maybe.
Oh, that's what my
Hopefully.
brother. That's what my brother did. He was a paint. He draws and stuff, and my father didn't allow him to go do that when he was young. So he went to architecture school, and now he retired when he was 55, and then he do photography and painting, and then he can even sell those things. I mean, not like he started when he was in his 20s, but he made enough money to retire at 55, and then he can, yeah, so I mean, you know, you want to guarantee
Yeah.
income when you were young, you do other things.
We are all back here? We are, right? 5, 11, and 12. bidirectional spectroscopy. It's going to be a little bit heavier, I think. A little bit more technical, using more qualitative introduction to light, which is going to serve as base for my subsequent lectures, and also will you study with ProBright. We also said, what did I say? About vibrational spectroscopy. I have to warm up for a second. We said that everything has thermal energy, has some thermal energy, because nothing can be at 0 Kelvin. That's not an allowed temperature. It's called 0 point energy. And everything vibrates, yeah? So from those vibrations and their energies, we can obtain chemical information. Those vibrations, and this is very important, are going to be between atoms. I put here some carbon compounds. Carbon is very versatile, can be arranged in different matters, yes. And each of those molecules that you see there have different shape, has different geometry, and different bondings. Some of the carbons are single bonded, double bonded, triple bonded, and then they have different hydrogens, different amount of hydrogens attached around. So that will give rise to a different vibration within each molecule. And hopefully, by sensing that, there are a couple of ways of doing that. We can tell what that molecule is made of, because each molecule is different. Each molecule has different atoms. Some molecules have the same atoms, but they are arranged differently. So that will give rise to different vibrational spectra. We go to the next slide. We have a less daunting molecule, which will be that as something like an oxygen molecule, a nitrogen molecule, hydrogen molecule, something like that. A molecule with 2 atoms, in which is pretty straightforward to begin to understand what a molecular vibration might be. And in the case of a diatomic molecule, there will be only one possible vibration, which will be what we call symmetrical stretching, which will be starting at an equilibrium position, in which the molecular bond length is set. Then the bond will vibrate around that point. So in a diatomic molecule, that can only happen with one atom moving away from each other or close with each other, yeah? Vibrating like that. That's a molecular vibration. It's called symmetrical stretching, and that vibration and any other vibration is going to have an energy. It can vibrate more strongly or less strongly. It's going to have an energy. That's going to have a range. We'll see that range is in the infrared. So it's a lower energetic process. And that range is going to be quantified. Meaning not all the range is going to be allowed. There is some energy that's allowed, and then there is another higher energy that is allowed, and so on. That's what we're going to be calling vibrational levels. Are energy levels within vibration. Single diatomic molecule can vibrate like this, right? If we attach another atom there, we get something like a carbon dioxide or a sulfur oxide molecule. In a carbon dioxide molecule, we'll have an oxygen, carbon in the middle, and another oxygen in line with the other. In a sulfur dioxide or something similar, we'll have a molecule with an angle at the bond, and then all of a sudden the molecule can vibrate in more ways. When you add another atom, then you can still have a symmetrical stretching. If you have one atom, two atoms, like moving away from the other one and then coming closer, it can vibrate like this in a symmetrical stretching. And then you can also have then an anti-symmetrical stretching in which one atom will vibrate getting closer to the other atom, while the other one will actually move away, so doing something like that, right? That's an anti-symmetrical stretching. This is a little convoluted, but I hope it makes sense. And then we'll have another vibration in a simple molecule like this, which is called a bending, in which the molecule can bend. Yeah. In actuality, the molecule will vibrate however it wants, but all the positions during the vibration and all the movement of the molecule can be mathematically described as a linear combination of those three vibrations on a three-atom molecule. It actually vibrates like this, right? Right? But that can be decomposed as this, and that. It follows for larger molecules. If you go one slide back, you're going to have a lot of vibrations. A lot of them, really. Some of them are going to be visible through Raman spectroscopy. Some of them are going to be visible through infrared spectroscopy, and some of them can be seen through both. And we'll see, we see from this slide and the next slide that molecules have different atoms. The atoms have different bonds depending on what the atoms are, depending on which chemical element they are, and even depending on which isotope they might be. Does everybody know what an isotope is? Everybody? Okay. They have a little bit different weight, yeah? So different elements have different weight. So the atoms are going to have different weight between different molecules, depending on which atoms are bonded to each other and the kind of bond they have. They are going to have a bond energy that's different between molecules, and then given the weight that they have, everything that's attached to them also matters. Given a reduced weight to the vibration, that's going to be different for each molecule. And at the end of the day, in theory, you'll have a different vibrational spectrum for everything out there that has molecules. Doesn't work for, I don't know, metals or atomic clouds in space. But as long as they are molecules, you can potentially get a very concise, precise, and unique spectrum for each molecule. So it's potentially very helpful for planetary exploration, right? Because we can measure whether that thing is water or pyroxene or whatever it is. But it can be also used for chemical processes or medicine. We do research on medicine things. Yeah. Here we have the first Raman spectrum of this lecture, and possibly the first one you've ever seen. And the first thing we can see is that it has a weird x-axis. That's usually in Raman shift. I will explain this later again. That's Raman shift. The unit is inverse centimeters, which is 1 over a length unit. So that's actually called wave number. And we use it like that because for Raman, we're going to be using different wavelengths, and then the x-axis become linear and transferable between wavelengths. If we were doing wavelengths instead of wave number, we'll get different Raman shifts for different things. Hopefully that become clear. I'll explain again. On the infrared, we'll see the same numbers. On infrared spectroscopy, we'll see the same numbers because we're actually seeing the same energies. In this spectrum here, that's the spectrum of water as seen from a distance. So what we see in there is the water spectrum, which is that broad thing on the right. That is the symmetrical and anti-symmetrical stretching of the H2O molecules. And then we see a little bump in the middle, broad bump, which is the bending of that molecule. And then since we are measuring at a distance, we see oxygen and nitrogen, which have very characteristic vibrational spectra at 1555 and 2331 per centimeters. And like I said, every molecule will have different spectrum. Going back to carbon, because it's nice to plot. And it can show the different shapes that materials can have. That's going to go for anything, from proteins to minerals to cellulose that the wood is made of. The molecules are going to be arranged in different ways, yeah, with atoms in different ways. So, for example, for things made of carbon, yeah, we can get graphite, has a different spectrum than that of diamond, and is made of carbon. And then, depending on how many layers of carbon you make your layers or carbon nanoballs of, or nanotubes, you'll get different vibrational spectra from those. Yeah, you'll get different spectra as well from different polymorphs of quartz, for example. Quartz can be quartz, the mineral quartz. Quartz can be glass, meaning instead of a crystal, arranged order of molecules to form a crystal. It can be a glass with amorphous, non-arranged, random orientated particles that will look like actually window glass. Yeah, it's actually basically silicon, it's like quartz glass. Yeah. It has another things, but more basically that. So that will be amorphous quartz. Yeah, have different spectrum than quartz. It'll have different spectrum than stishovite, which is another mineral. That's also silicon oxide, or tridymite. Those form in meteorite impacts. And they all have different spectrum. Different minerals will have different spectrum, different ices. Yeah? If we were to go ahead and measure something on icy moons and look for life in Europa, for example, and we're interested in looking for water, the spectrum of ice will look close to that one that we saw of water. Not the same, but close. So we could tell that we have hydrogen and oxygen bound together. Ice can potentially have, depending on the pressure and the temperature, different phases, different arrangements. All those will have different Raman spectrum as well. Is that more or less clear? So that will, we go to the next slide, that will give rise to the phenomena that we use for infrared spectroscopy and Raman spectroscopy. Both of them are vibrational energies within molecules, right? Infrared spectroscopy is based on absorption. This is very important. To perform infrared spectroscopy, you need your material, whatever you want to study, to absorb the light that you're sending, and then you need to measure what is going through, right? So that's typically done by shining a light source that's white, quote white, meaning that has a broad range of wavelengths. On the range of wavelengths of those vibrational energies, and then you shine it through your sample, you measure on the other side, and then you'll see whatever you send, the broad spectrum you send, with some dips on it, which are the dips created by the vibrations energizing themselves. When you shine the light, photons go through, the vibration will be at one energy level, and some photon will hit it and can potentially get absorbed. The vibrational energy can get excited into a higher energy level, so then that photon coming in will basically disappear. So when you measure your spectrum at the end, you will see dips on it. That will be infrared spectroscopy, and is based on absorption. Raman spectroscopy is looking at the same thing, but it's based on scattering, which, like we said, is the change of path that light might undergo when it interacts with material. Most of the scattering out there is basically light bouncing off surfaces with no energy exchange. If you have a laser pointer that's green and you shoot at the wall with it, most of the light that gets scattered from there is going to be green, the same green that you sent in. The same happens for all the wavelengths. A small fraction of it, typically 1 out of 10 million photons or less, might undergo inelastic scattering, which is going to be change of direction with an exchange of energy. And the effect that will give rise to the Raman effect. The vibrational energies are constrained between 0 and that 4160 inverse centimeters, which is going to be the highest energy. That is that of the hydrogen atom, light hydrogen. If you put deuterium in there, that will change actually a lot. The ratio of the weight is going to be very big. And that's going to be at 2.5 micron or 4160 inverse wave numbers in wave number, or 0.521 electron volts. We go to the next slide. We have this Jablonski diagram, it's called, which is an energy level diagram to try to make sense of vibrational energies and scattering, and this one has also fluorescence, because we're going to study a little bit of fluorescence. On the bottom left of the plot, we have infrared and Raman, and then we have a y-axis which says S0, S1, and S2. Those are electronic excited states, and then if we see there on the bottom, this be nicer with a screen. Here we have nu1, nu2, nu3, which will be a representation of vibrational energies being a lot smaller than those more energetic electronic transitions. So given a vibration that has some potential vibrational energies, we'll go back to our very simple, the atomic molecule will have a basic vibration, ground state is called, and then it will have excited ones, yeah? So that will be the bottom line, and then the 1, 2, and 3, yeah? So on the normal scattering, that is called Rayleigh scattering, which is the most typically occurring, the photons will bump off the material with no energy exchange, and those photons that we are going to be dealing with for Raman are going to be ultraviolet, visible, or infrared, but they are going to be a lot more energy than the vibrational energies. So they are going to bump the vibration into a non-allowed, it's called, into a quantum mechanical non-allowed vibrational state where the vibration cannot exist. So it will immediatly, in femtoseconds, go back to where it was. To what it was when it's Rayleigh scattering, but sometimes in the Raman effect, you can actually go to one of the other vibrational states. So when you get light shining on something, if you measure what's coming off, you can potentially see those changes on the wavelength that you are seeing. And that will be the Raman effect. We said about the absorption, yeah? We have it on the bottom left. On the absorption, you will send a broad beam with the infrared light that matches the energies. That will get absorbed, and that will give, those arrows that are there, they will get directly absorbed during absorption, yeah? During scattering, we'll get a virtual state, and then a deflection of the photon, and then a change or not if it's Rayleigh, and yes if it's Raman, where the scattered photon is going to have different energy. If the molecule is on ground state and gets excited, the photon will have less energy. If the molecule was excited and it actually relaxed when interacted with the photon, then your photon will have more energy than it came in with. That happens, that is called anti-Stokes Raman, the other one is called Stokes Raman. At normal temperatures, the Stokes, so the fact that you're losing energy when you Raman interact with materials, you're losing energy is more common. And Raman is done with typically lasers, because if you shine white light, then you'll get a range of shifts, yeah, like changes in wavelength across the white spectrum. So it will be overlapped with the white spectrum, so you couldn't see anything. So initially, when they saw it first, they took sunlight and they sent it to a monochromator, which is an spectrometer reverse, meant to separate and end up with a very narrow light beam. So then when you have a very narrow light beam, that you know what it is, and if you send something that's green, for example, and you get a scattered photon that's red, and you can measure with your spectrometer that's red, you're going to know it has less energy. You're going to know from the wavelength how much less energy that has. You're going to know its wave number. So then you are going to know those vibrational energies. So, and then you're going to get a scattering spectrum that's going to have positive. We're going to say we typically use lasers because they are very monochromatic and very intense, and then measure what comes out of there. We'll take a spectrum of that, then we'll see a black background. We'll block the laser because it's going to be very bright. We'll use a filter to block the laser, and then we'll get peaks on whatever those shifted laser wavelength. We call it shifted, but whatever those energy exchange photons that come out. Vibrational spectroscopy, like I said, comes from vibrations, gives you information about chemical bonds between the atoms and their structure. So it's very useful to tell when things are off. Yeah? So molecular bonds are unions between atoms. they usually happen by sharing electrons. They can do so in different ways, with ionic bonding, valence bonding, and metallic bonding. If you stretch a bond, you provide energy, it will vibrate. That's what we do. And if we distort molecules, like we do with light, that's what we do. So a chemical bond is the attraction force between atoms. Yeah? When you have two or more atoms, of course. Yeah. If you have only one atom, there's no molecule. There won't be vibrational spectroscopy. We'll see later that we will be able to get an atomic spectrum with one atom, but there's nothing to vibrate there. So the bonds are characterized with a length. Yeah. And a bond strength. Yeah. So the distance is, the bond distance is the equilibrium distance. So you think will vibrate from there. The bond can be seen using classical treatment as in a spring, in which you stretch the molecule and it will basically vibrate. We know that everything is going to be quantified, so it's not just going to basically vibrate. And then that's going to have an energy distribution, in which when you compress the molecule too much, it's going to become harder and harder, and you stretch and stretch, it's going to get harder and harder until it breaks. Then there will be a vibration there. You'll have two atoms or more. And I did hint at this earlier. You'll distort the molecule, right? With heat or light or electricity or whatever it is, it will vibrate in all kind of ways, however you want. Yeah. What I said earlier with the fingers on a 3-atomic molecule, and the complex movement is going to be a linear combination, superposition of vibrational modes, which are called normal modes of vibration, and those give information about the chemical bond. And next slide is even a little bit more complicated, but it's a mathematical explanation using classical treatment on how that will work. You have some masses, and then a bond distance, and a center of mass located where one mass plus the other divided by the distance. The mass is going to be, the center of mass is going to be closer to the heavier thing, but it's going to be the representation of the whole weight of the molecule, and then you'll have a vibration. If you have two atoms, that will be a symmetrical stretching, which will be a little shift from the equilibrium position from that position. The bond length is the total distance, and then you have some displacements. If you take the momentum and the Hooke's law, which is the law for basically springs, and you treat the bond as a spring with a constant, which is that K, which is the force constant of the spring, which can be correlated to the force constant of the atomic bond, and the Newton's law, which is force equals mass multiplied by acceleration, which is the second derivative of the displacement versus time. Yeah, so it's distance versus times is distance versus times speed, and second derivative of distance versus time will be acceleration, so the change in speed. So if you have a total stretch and you substitute, you get those equations in the bottom. The force can be expressed as the force constant multiplied by the displacement, and the potential energy there, which is the energy that can be stored during the stretch. Potential energy is basically the energy that can be stored. There is electric potential energy that is called voltage. There is gravitational potential energy that is used on dams to produce electricity, letting water fall. The water will have more gravitational potential energy. Potential is basically that can happen, yeah. The power to happen. Has more potential energy when it's higher than when it's lower. So if you let it fall, so the spring will have also potential energy. You stretch it, it will hold that energy in the metal atoms trying to come back to where they were. So that the potential energy for that will be a half of the constant multiplied by the square of the displacement. You keep substituting, and you get to a differential equation, which is an equation that has derivatives on it. That can be expressed as a function of the displacement and the reduced mass of the atomic bond, and then the solution of that, doing mathematical treatment that is out of the scope of this class. You'll get wave functions. Wave functions can be mathematically expressed as sinusoidal waves, yeah, rotation expressions, which are the sinusoidal, cosinoidal, and tangent functions, which will solve the position with an amplitude, and then a oscillating function by that is only a function of the phase and the time. And if you have a spring pulling from two masses and you let it float in space, it will vibrate like that, yeah? So that's going to be a cyclical function for the position of each of the atoms. And those functions will use this omega unit, which is the rotational value on a 2p, 2 pi circle. And that's the frequency, vibrational frequency. It's going to be a function of the atomic, of the bond strength, yeah? So the spring strength, the atomic bond strength, and also the reduced mass. That's that omega equals k divided by the reduced mass, the square root of that. And you want to check in Wikipedia, there's well, there used to be, when I took this, I think it's still there. There used to be a little explanation of how that equation is resolved, but like I said, that's beyond the scope of this class. So the takeout message from this slide will be that the vibrational frequency is going to be a function of the strength, yeah, and the reduced mass. On the next slide, we have the same, yeah, the vibration. That concept is very important too. And we have a plot of its vibrational energy. The total energy at each time is going to be a combination of the potential energy, the potential for energy to happen, and the kinetic, so moving energy that each atom is going to have. And that's going to plot as, that kind of well shape when you have the displacement on the x energy and the potential energy on the y-axis. At the bond length, the potential energy will be minimized, will be where it's closer to equilibrium, yeah, where less potential energy there is. You stretch it from there, you'll have more potential energy towards the side, and then it will vibrate from there with potential energy going up and down that well, and the kinetic energy of the thing vibrating when it's symmetrically, as you see the sum of them. I think it's the U and K there. For a vibrational level that we are going to see are represented as horizontal lines in this plot, because everything is quantified and we cannot have all the energies on this curve. We are going to have some of them, both in potential energy and both in kinetic energy. So the vibrational energy are going to be different. The rotational vibrational frequency, which is in that orange box, is referring to rotations, yeah. So it's of course multiplied by 2 pi, but it can be also expressed as hertz, yeah, which is the inverse of time, and that goes related to 2 pi, right? And we'll see that omega typically as the rotational frequency, and then nu later as the hertz vibrational frequency. We are not going to get into the next slide, but that will be the quantum mechanical approach. That goes way beyond what I can explain and way beyond the scope of this class. But it's the quantum mechanical treatment of that spring atom that we envision. If you do it classically, it's easier to understand the potential energy. When it's quantum mechanics, you had to get a Schrodinger equation and you had to solve another equation. Gets a lot more complicated, and then you get corresponding energy levels at the bottom. That one is important, which are that H or H with a bar, which is the Planck constant. I did say earlier that on the black body radiation we have a corpus light, right? I did say that when they try to replicate that corpus light through experiments, they found out it couldn't make sense unless you assume that the energy is distributed in discrete packages. So when they did that, everything makes sense. That was Planck. And the number of the packages of energy that he got mathematically were named Planck constant. That's that H with the bar. That's the Planck constant. It can be with the bar when it has the 2 pi in it, or without the bar when it doesn't have the 2 pi in it. When it has the 2 pi, when it's the H bar, it's going to have the vibrational frequency, rotational. When it only has when it doesn't have the bar, it's going to have the hertz, the nu, and then a quantum number. And some of the numbers there, the quantum number is the n. In quantum physics, everything is quantified, so all the energy is called by quantum numbers. There are integers, called regular integers, natural numbers that increase, and energies are only going to be, you change that number by discrete values, or the energy, the En, for each energy, you're going to get one value. Yeah, so you're going to get, given space by the Planck constant, you're going to get different spaces. And then you have from Wikipedia here on the right some representations that people can make to try to understand quantum mechanics, such as waves, when it's actually probabilities of finding things in different places, and everything is waves and particles, and we get probability densities. We'll move to the next slide. We're going to make it a little easier now, I think. We're going to see how vibrational energies can change when we change molecules. Different molecules are going to have different vibrational spectrum. But most of the influence on the vibrational energy are going to be given by the two atoms that are bonded. Yeah. I did say that you're going to have some influence from the surrounding atoms that form the molecule. What is that?
We don't know.
Oh, okay.
Me.
Okay, we'll take a break.
Where it is.
Looks like it's still going. Yeah, no, it's fine.
Okay, everything okay?
Yeah.
What was I saying? So most of the influence on the vibrational energy comes from the next together atoms, and there's some influence from surrounding atoms. We have some examples here. For the oxygen hydrogen bond, we get that 34 to 3700. That's going to be all the water frequencies. If you put something heavier, such as nitrogen, the vibration becomes a little bit less energetic, a little bit. If you put something even heavier around carbon, such as carbon, then you'll get 2800 to 3000. We'll see OH stretching for water, NH stretching for ammonia, and things like that, and CH stretching for everything organic. Our proteins, alcohols, everything has CH on it, which is a lot of things. Everything that has CH on it is probably going to have CO as well. That's going to have lower energy, heavier atoms. And then if you put even heavier, and you put carbon to carbon, even heavier, you get closer to zero. If you start putting metals in there and heavier atoms, you get actually really close to zero. The mass effects, yeah. I did very tangentially say earlier that if you have a hydrogen molecule with two hydrogen atoms, you get a 4660, yeah. Assuming it's light hydrogen, if you put a deuterium there, that becomes 3632. Because one atom is going to be pretty much double the weight, because it's going to have a neutron and a proton. So it's going to be double the weight. The whole reduced mass is going to increase a lot. So the vibration energy is going to reduce a lot for the same vibration. Even if you put two deuteriums, it's going to go down more than 1,000. And the chemical bond does not change too much. The mass changes, yeah, but the chemical bond doesn't change too much when you do that, yeah, when you put deuterium as opposed to hydrogen. The electromagnetic forces are basically the same. If you substitute with isotopes, yeah, such as in deuterium, the force constant is going to be the same, and the difference is going to be due to the change in mass. Yeah. So that can be used in Raman and infrared. And actually, a lot of the knowledge we have about molecules comes from vibrational spectroscopy itself, because you can put some different isotopes and see how it changes. So you can see from whatever molecule that has this isotope or this other one, how it changes. Yeah. So you can see if it's bending or symmetrical, and you can actually measure bond lengths and bond orientations. And you can do that. Of course, you can do Raman and infrared in liquid, gases, and solids. How much time do I have? If you change the next slide, we see what will happen if you change the atomic bond. Yeah. I have how many more slides? 5 more. We'll continue the next day. We'll go back a little bit with whatever questions you might have, and I'll repeat again. Hopefully it becomes a lot more clear. But if we change the force constant, so now instead of changing masses of atoms, we're going to change the force. Yeah. So we have these hydrogen acids. Yeah. And if we change maybe from how is this called, fluoridic acid to chlorhydric, is that the name? sorry, chemist. But hydrogen bonded to fluorine, bromine, and iodine. The electromagnetic force between the two elements is going to be different because the elements are different. In the previous slide we had hydrogen, same atom really, different mass, but now we have different different forces for the same kind of bond, yeah, and the same kind of hydrogen atom on one side of it, yeah. So we can see that changes a lot too, right? There is a little bit of mass influence here because of course the fluorine, bromine, iodine, they don't weigh the same, but there's a large change for 4,000 to 2,000, almost 2,000 weight numbers. We saw that the change in mass for the hydrogen made out of deuterium was 1,000. So we see that the effect of force constant can be potentially higher. And in this case, this is due because the bond gets weaker as you go down the periodic table. The fluorine is more electronegative than chlorine, and so fluorine and chlorine are actually very dangerous for us, very reactive. They attach to the hydrogen really fast. And in the next slide, you can combine a little bit of both. You can change, with respect to the previous slide, you can remove the hydrogen and make the atomic molecules of those 4 elements that are going to have more stronger bond for the fluorine, weaker bond for the iodine. We can see that it changes a whole lot, yeah, when both the mass and the force constant are changed, yeah. When you get heavier things, then you start getting closer to 0, right? And then the next slide, and I do have 4 more. Don't worry. Just to review, the vibrational frequency depends on the mass of the atoms, on the strength between the atoms, and then the number of vibrational modes is going to depend on how many atoms are in the molecule. We said that one atom is not going to have a vibrational spectrum. 2 atoms in the molecule is going to make a very simple vibrational spectrum. Then if we put more, we get more vibrations. If we get an organic molecule, will get more complicated, a lot more vibrations, a lot more peaks when we see the spectra. And keep in mind that crystals will also have some extra vibrational spectra because waves can travel in the crystal on the change of atoms. On the next slide, we see a very simple representation of an angular triatomic molecule with a symmetric stretch, an anti-symmetric stretch, and a symmetric bending. And the vibrational frequencies, those vibrations will have for water and nitric oxide. And for linear molecules, that's going to be a little bit different. Of course, the bending is going to be what we call degenerated. It doesn't matter which way it bends, it can bend actually different ways. And then on the next slides, up to the last one, the one from the last, we see different types of vibrations. There are many more, I think. That's the whole theory of group theory is called, where actually vibrational modes or of solids can be theoretically calculated from the atoms that makes the solids to all these movements. And then the last slide says that we are going to have a number of vibrations on each molecule that depends on the number of atoms that we have. So the total number is going to be 3n minus 6 unless the molecule is linear, in which we're going to have two degenerate states, and it's going to be 3n minus 5. And it's exactly 1. Kudos to me. We'll meet each other on Thursday at 10:30 here.